Time for us to talk about planet atmospheres and about atmospheres in general. We'll get to specifics about each planet's atmosphere as we go through the planets, but there are some general characteristics of atmospheres that will help us in discussing each planet separately. We've again observed the terrestrial planets and the gas giant planets. The atmospheres of the outer planets are much, much thicker than the atmospheres of the terrestrial planets. But again, the spacing here with the terrestrial planets being close to the sun raises the temperature of the terrestrial planets compared to the Jovian planets. That has a major effect on what gases are in the atmospheres of the terrestrial planets versus the Jovian planets. So on our astronomynotes.com, the textbook that I'm using in my class, there's a link for planet atmospheres. So you should click on that link and inspect the data that's given there and take a look at the atmospheric pressures for the planets. That's worth just sort of gaining a general understanding, as well as the composition of the atmospheres. And there's a long list of components of the atmospheres in this table. Just focus on the primary components. So we'll discuss that in class for my students. So the planet atmosphere has a benefit for, say, the Earth. Our atmosphere acts like a blanket, and when we're facing away from the sun, if we did not have an atmosphere, our temperature would drop much more at night than what it does. Take note of the moon. Now, the moon's a little different. It doesn't have a 24-hour rotation period, much slower spinning. But in the sunlight, we have 250 degrees Fahrenheit in the daytime, and then minus 380 degrees Fahrenheit at night. So a wild swing in temperatures. And for those future colonists of the moon, that's something that they'll have to protect themselves against, this wide range in temperatures. Our atmosphere not only stabilizes our temperature, but it also protects us from high energy light, from gamma rays, X-rays, and ultraviolet light. We have an ozone layer that we need to preserve that is useful, for example, in absorbing the ultraviolet light. We have atmospheric pressure. Pressure is needed to have liquid water on a surface of a planet. So our atmosphere provides that. On Earth we have liquid water, and the atmosphere allows nutrients to mix across the planet to be transported. For the case of the Earth, oxygen. You don't have to go to Nebraska to breathe oxygen versus North Dakota. It's available all around the Earth and is transported by motion of winds in our atmosphere. So what considerations do we have for retaining certain molecules in an atmosphere? Here we have a chart of the speed of molecules, and you don't have to memorize the numbers that are presented here, but what we're looking at is difference in temperature. So if we plot here, the black line is really cold, the blue is really hot, and the red is in between. What we observe is the speed of the molecules on this horizontal scale increases. As the temperature goes up, the speed of the molecules goes up. That's probably not too surprising. High temperature you probably associate with more energy, and that is the case. But we have here, for one particular type of molecule, we have a increase in the speed where this peak occurs, and many more molecules at the high temperature traveling at a very notable speed. At the cold temperatures, the molecules are less spread out in their speeds, and the peak speed is at a lower number. So that's one fact about molecules. If the temperature is higher, they travel faster. If the temperature is higher, the molecule travels faster. So to retain an atmosphere, we want to have molecules that are below escape velocity. We want the speed of the molecule to not exceed the speed necessary to escape the gravity of the planet. Well, the gravity of the planet depends on our capital G constant, the mass of the gas, the mass of the planet, and the radius of the planet squared. We're not going to do any calculations here, but you should know that different planets have different masses, different planets have different radii, and this force of gravity changes from one planet to another. Just in general, which of the terrestrial planets do you think has the largest value for its gravitational force on its atmosphere? If you guess the Earth, you'd be correct. The Earth has the largest mass of the terrestrial planets. The radius is not that much different for, say, Earth and Venus, but it's really the mass that kind of dominates the effect. Mercury has the least mass of the 4 terrestrial planets, and it has the least atmosphere. And there's another reason it does, besides just low mass. But for the planets or moons that we have listed here, escape velocity for the Earth, 11,200 meters per second. That's about 25,000 miles an hour. We talked that the orbit speed is about 17,000 miles per hour in low Earth orbit. So the sense of things is correct here. Escape velocity is higher than the circular velocity. The Moon, only 2,400 meters per second. The Moon has much less mass than the Earth. It's a little smaller also, that makes gravity stronger, but the mass is the primary effect here. Mars, 5,000, about half the speed of the Earth. Jupiter, 60,000 meters per second. Jupiter has a very large mass. Its escape velocity is very large. It has a large force of gravity on the molecules in its atmosphere. So, are we going to retain an atmosphere? Well, it depends on how fast they're going, and that will depend on the type of molecule and the temperature. We talked about the temperature effect earlier, but it turns out there's a mass effect of the molecules as well. The lighter molecules travel much faster than the heavier molecules. The lighter molecules travel much faster than the heavier molecules. And we talked about this, hotter gas, the molecules travel faster. It's worth noting in our atmosphere, in the Earth's atmosphere, room temperature, so if we calculate nitrogen, the average speed of a nitrogen molecule is a little over 1,000 miles an hour. What would you like to have hit your face at 1,000 miles an hour? Well, it better be something that's very small and does not have much mass, and that's the nitrogen molecule, or the oxygen or carbon dioxide, H2O, water vapor molecules in our atmosphere. Ballpark, they're traveling around the 1,000 mile per hour number, and because they are very light, it does not, they don't break through your skin, but it gives us an air pressure having this high speed, and things do bounce around and create a pressure. But overall trend, is a planet going to retain an atmosphere? It has trouble retaining the light molecules. Say the Earth has trouble retaining hydrogen, helium, because those light molecules travel fast, and the Earth's escape velocity is not terribly high. We have a reasonable temperature here, so low mass, reasonable temperature, the molecules are traveling at fast speed, and the Earth does not have a big pull of gravity. So in fact, we've lost hydrogen and helium from our atmosphere. The speed of noble gas here, and taking a fixed noble gas, well, on one particular curve, a fixed noble gas of the blue being helium, then neon, the yellow, argon, and xenon. These have different masses, and pretty much these numbers on the superscripts are a gauge of the mass of a particular molecule, with helium being the least mass. And as I said in the previous slide, if the mass is small, the velocity is high. So here's helium, and it gets to the place above the escape velocity for the Earth. This is one particular temperature, don't need to know what the number is, but for a constant temperature, if the mass of the molecule is smaller, the molecule is traveling faster. If the mass of the molecule is smaller, the molecule is traveling faster. Here we have, again, a fixed temperature, and taking a look at oxygen, methane, ammonia, carbon dioxide, and what we see is, again, the same trend. The molecules that are heavier, where there's more mass, travels slower, so this purple line, and the molecule that's simpler with less mass, the nitrogen and 3 hydrogens in the molecule, that has the highest speed. And for like the terrestrial planets, the molecules with high speed are the ones most likely to leave the planet. Okay, so that's the planetary atmospheres. We'll discuss more of that in class. In my class, we have a lab that deals with that. But pressure times volume equals a constant times temperature. This is a gas law that relates pressure, the volume of the container for the gas, some constant, and then temperature. And if we would solve for pressure here, divide both sides by volume, what will make the pressure higher? What will make the pressure higher? Well, if the temperature is higher, the gas molecules are moving faster, they collide more violently, and that creates a higher pressure. If we compress the gas into a smaller volume, the pressure becomes higher. And if you could think about a balloon, if you would press in on a balloon and apply force to the balloon surface, as that volume gets smaller, more force is required to compress the balloon. So if the volume is smaller, the pressure is higher. This constant can be discussed just a little bit. If we would have more particles of gas in the container, the pressure will be higher. More particles leads to more collisions and leads to more force on the walls of the container, and the pressure would be higher. So things that make the pressure higher: more molecules, higher temperature, and smaller volume. Now, hydrostatic equilibrium, there's a balance in our atmosphere. There's a balance. Gravity would like to pull all the molecules down to the surface of the Earth and make just a thin layer of gas molecules. Perhaps they would condense into some liquid at the surface of the Earth, but gravity would like to pull things down. What balances gravity? Well, it's the collision between the molecules that creates an upward force that suspends our atmosphere, maintains our atmosphere up above the ground level. This would really be a much different planet if there was no thickness to our atmosphere and we needed atmosphere to take in oxygen. We would have to slide along the ground and stay in that very thin atmosphere along the ground. So it's good that we have hydrostatic equilibrium. There's a balance. The force of gravity downward, the force of the collisions of the gas molecules creates an upward lift, and we have some stability to our atmosphere. Our atmosphere does get thinner as we go higher, but this hydrostatic equilibrium maintains a certain thickness for our atmosphere. Roughly 50 miles or so is notable atmosphere. The other thing I probably should mention before I forget: does the Earth have a top for its atmosphere? Is there a certain place where as rockets go into space, they kind of pop up out of the atmosphere, similar to a fish jumping out of water? And the answer is no. Gases do not have a top surface. That distinguishes them from liquids. Liquids do have a top surface, but a gas just gets thinner and thinner and thinner and thinner. There is no definite boundary for the top of the atmosphere of the Earth. Then surface temperature relates to atmosphere. In terms of balancing energy, sunlight comes in, the Earth radiates energy back out into space, and then our atmosphere affects how this energy in the infrared gets back out into space. You know that from our talk of telescopes that our atmosphere absorbs in the infrared. So the temperature of the Earth is such that it emits infrared primarily back trying to get out into space, and the atmosphere acts like a blanket and keeps some of that infrared energy near the Earth instead of letting it go out into space. So we have an equilibrium temperature about 50 degrees Fahrenheit for a global average for the Earth, and the number escapes me. If we didn't have an atmosphere, I think it's like 40 or 50 degrees colder for maybe even more than that for the average temperature of the Earth. This has a major effect that I personally like the summer temperatures a little more than the winter temperatures. If we did not have an atmosphere blocking the leaking of infrared light, it would be much colder for the global average of the Earth. You can think also about a cold day in January, and then it comes nighttime. What is going to which is going to be the colder night, when the sky is clear or the sky is cloudy? Well, perhaps you've heard the phrase clear and cold, clear and cold. Clouds absorb extra infrared energy, and then that's re-radiated back down to the ground. The clouds act like an extra blanket other than just the atmosphere. If the atmosphere is clear, if there are no clouds, it's easier for the infrared energy to get out into space, and the Earth loses more energy at the night temperature becomes colder. There's a technical term for how much energy is absorbed or not absorbed by a planet, and the energy that's reflected, that's not absorbed, is called the albedo. And we'll study the albedo numbers for the planets as we go through them in our solar system. So there's a little tour of atmospheres. In retaining an atmosphere, the lighter molecules travel faster. They're harder to retain. Molecules are harder to retain if the temperature is higher. Molecules are harder to retain if the mass of the planet is smaller. So terrestrial planets have not been able to retain hydrogen and helium. The Jovian planets, it's colder in the outer solar system. They have more mass. They're able to retain the hydrogen and helium. We have a relationship between pressure, volume, number of particles, and temperature. The pressure goes up if there are more particles. The pressure goes up if the temperature is higher and the collisions are more violent. And the pressure goes up if the volume becomes smaller, if we try to pack those molecules in a smaller space. We have hydrostatic equilibrium. Gravity's trying to pull the atmosphere down. The collisions between the molecules provide an upward force that keeps the atmosphere with some thickness. We don't have an atmosphere that's just coating the rocks of the Earth. And it's about 50, 60 miles up where meteors, as the little grain of sand comes into our atmosphere, they have friction with the air. The air molecules receive energy and then emit light. It's the air molecules emitting light for a meteor, not the little grain of sand itself. So keep reading on that and ask some questions.